So, so thanks a lot. First of all, I want to thank Raki for supporting me and giving me the opportunity to be here. I will present you our work on detecting outages at peering infrastructures by parsing publicly available routing information. And in particular, I will focus on two types of infrastructures, internet exchange points and carrier-neutral colocation facilities, both of which are crucial components of today's interconnection ecosystem. The largest of these infrastructures support hundreds of thousands of peerings. So the availability of these infrastructures needs to be almost constant. The operators try to provide SLAs of 4 nines in the case of IXPs or 5 nines in the case of colocation facilities, which translates to maximum 5 minutes of downtime per year. And although these infrastructures are very well maintained and provisioned, outages still happen for a variety of reasons, such as power cuts, human errors, misconfigurations. So we've seen from news reports that when these incidents happen, the impact on upper layer services and applications can be severe. We had disruptions of banking services, of communications, even aviation services have been affected. Therefore, it is very important to have the ability to detect and monitoring such outages to improve our situational awareness and develop the appropriate risk assessment and mitigation techniques. However, today, the current state of the art is a bit manual. So network operators largely rely on their infrastructure providers to notify them when something goes wrong. And if they are not notified for any reason, they resort in asking each other in mailing lists whether they experience the same problems in the same locations, which is obviously not the best way to react timely in the face of failures. And we have this problem because the ecosystem is very complicated. So these infrastructures are tightly interdependent and symbiotic. In this figure here, we see the topology of France IX, a large IXP in Paris. So it has distributed its peering fabric across multiple facilities all over the Paris metropolitan area. And when something fails in this setup, it's hard to distinguish the epicenter of the outage from the cascading effects. And to make things more complicated, we have practices such as remote peering that extend the reach of IXPs far beyond their local markets. So here we see in the map the footprint of the Amsterdam Internet Exchange, which is literally global. And again, when something goes wrong, the implications can be tricky to predict. So we try to tackle these challenges by having these research goals. First of all, we want to develop a technique that will automate the detection of outages at colocation facilities and IXPs in a timely manner. We want to be able to distinguish the source of an outage from the cascading effects and have the ability to track the evolution of the outage in order to determine how long it lasts, what is the impact on the routing paths, and what is the geographic scope of the affected networks. And these goals are far from trivial, and I'll try to explain the challenges through a toy example, which is based on an actual incident. So we have 4 AESs here, interconnected through 4 different facilities and 1 IXP. And when everything works normally, AS2, which is our vantage point, reaches AS0 through facility 2 and the IXP. Now, when facility 2 fails at some point, the AESs reroute the path through facility 1. And the first thing to note here is that the AES hopes remain exactly the same. So we need to have the ability to observe the paths between AESs, not at the AES level only, but also at the infrastructure level. But even if we have this ability, we may still not be able to distinguish exactly the source of an outage. So in this example here, we have vantage point at AS2, and AS2 observes that both facility 2 and the IXP disappeared from the path. So the outage can be in either of these infrastructures. And to distinguish exactly the source of the outage, we need to combine and correlate the views from multiple vantage points, which obviously requires a large number of measurements. And again, we need a large number of measurements because we need to continuously monitor the routing system in order to compare the paths before, during, and after an outage. So we have these three requirements that are seemingly contradictory because of the limitations of our measurement data sources. So on the one hand, we have BGP measurements, let's say from route views and write trees, which are lightweight, so they allow us to continuously monitor the paths through multiple vantage points, but the paths are at the AS level. On the other hand, we have trace route measurements through, let's say, RIPE Atlas, which give us a very good granularity at IP level that we can map to IXPs or facilities, but they are expensive. And especially for the scope and the scale of the study, the cost of these types of measurement campaigns are prohibitive. So somehow we need to combine the lightweight measurement of BGP data with the granularity of trace route data. And in this work, our intuition is that, yes, indeed, BGP is an information hiding protocol, but the ACE path is not the only BGP attribute that encodes topological data. We also have the communities attribute, which is optional, but it's becoming increasingly popular. In this RIPE meeting, for instance, we saw earlier presentations about black holing or graceful BGP shutdowns. And one very popular use case of communities is the annotation of the ingress point where a prefix has been received. So if, let's say, AS2 uses the community 200 to annotate the ingress point, facility 2 as the ingress point where it receives a path from AS1, we can reconstruct the infrastructure level hops. And by gradually doing it through collecting data from multiple vantage points, we can collect the traversed infrastructures for all the ASs that we want to study. And if we monitor how these communities change, we can capture path changes at these infrastructures, even when the AS level paths remain exactly the same. Now, one of the problems is that communities are not standardized. It's possibly the only BGP attribute without standardized semantics. But fortunately, many operators provide public documentation in their WHOIS records or the websites. So we have developed some natural language parsing tools to extract these documentations. And we have created a dictionary of over 3,000 community values that provide ingress point annotation at 3 levels of granularity: city level, IXP level, and facility level. On the map, you see the geographic coverage of these communities. It's quite widespread. And although it is, these communities are just by less than 500 ASs, these ASs are quite large. They are present at hundreds of facilities and IXPs, and they have thousands of links. So we can map at least one traverse facility for half of the IPv4 paths and 1/3 of the IPv6 paths in route views and write trees. And we can track the fate of 1/4 of the facilities in PeeringDB, and importantly, 98% of the facilities with more than 20 members, which are the most prominent ones, right? So by having this dictionary, we can start doing the actual detection. So let's say that we want to monitor facility 2. The first step that we do is that we collect all the BGP paths that have annotated, that are annotated with communities of facility 2. On the plot, we see the number of such paths across time, and we monitor these paths for fluctuations. So, and fluctuations means that we try to find when we have changes in the communities attribute that indicate deviations away from our target facility. And when we have time periods where we have multiple concurrent community changes, then we have an indication that something happened at this particular location. And this can be, let's say, a partial outage, because the paths don't go all the way down to 0, but we have a significant fluctuation. But it also may be some depeering between large ASs or some major routing policy change. So we trigger a signal investigation process, which is a very involved process. I invite you to read the paper for all the details. I have a link at the end of this presentation. But essentially, we run a few targeted active measurements guided from the BGP hints. and we study how disjoint are the affected paths and how many ASs and how many links they involve. And through this process, we can determine the root cause of the signal, and if the root cause is an outage, we continue monitoring the community values, and we infer that the outage has been resolved when the majority of the paths return back to the original location. So again, this whole process is more complicated because the community for our location that we monitor may be affected by outages in facilities further away. So for instance, here we see that link spans may be affected by outages in one of its affiliated facilities. And we disambiguate such signals through studying the paths not in an aggregated manner, but at the granularity of separate AS to facility collocations, as I show on the right-hand side plot. Again, this is a more complicated process, but it allows us to accurately pinpoint the source of the outage. And essentially, this technique enables us to denoise the BGP routing activity that happens due to the normal routing dynamics from the dynamics that are caused by an outage. So here we see an outage that happened in France IX at the point of the gray bar. And I plot with blue the BGP updates, with red the BGP withdrawals, and with purple the state changes. And as you can see, at the point of the outage, we don't get a strong signal that something happened. But when we filter the paths based on the communities that annotate France IX as the ingress point, we have a very strong signal, which allows us to trigger the investigation process and localize the outage accurately. So we have applied this technique in 5 years of historical BGP data, and we were able to find almost 160 outages, most of which were not widely reported. We tried to validate them through a series of means, such as status report in network operating centers, direct communication with operators, and social media posts. We found we have pretty good accuracy. The few misinferences that we had were actually fiber cuts, very close to the infrastructures. And we missed only a few partial outages that did not result in a signal of high magnitude. In 70% of the cases where we had failures in facilities, the uptime went below the promised 5 nines, and even in 5%, it went below the 3 nines of uptime with very clear implications. I don't want to expand on that. And we also used active trace routes to assess the geographical scope and the impact on end-to-end latencies. So here we have an example of an outage at the AM6 Internet Exchange in 2015. We see that due to remote peering, over half of the affected links are in a different country, and 20% are even in a different continent. And we observe a 50% increase of the paths with latencies over 100 milliseconds, which obviously affects the upper layer applications. So to conclude, we developed a new technique that allows us to timely and accurately infer outages at IXPs and colocation facilities. We have seen that the majority of these outages are not widely reported. And we have also seen evidence that remote peering, let's say, globalizes the impact, amplifies the impact of localized events. And lastly, we hope that through this approach, we provide hard evidence to operators and researchers to help them improve the accountability, transparency, and develop new mitigation techniques to improve the peering ecosystem. Thank you very much. I'm ready to accept your questions.
All right. Any question? Second time? Last time? Okay. All right. Thank you
very much.
All right, let's move on to the next item on our agenda this morning, which is about IXP